Okay guys, now that we know basically how a single phase transformer works, we are going to do a quick example so you guys have a better understanding on how to do some basic calculation. Okay, um, this example will be based on the assumption that this would be an ideal transformer, which means that all the energy that is transferred from one side to another side would be 100%. So let's assume that this transformer do not have power loss, so it's not a real example. Okay, it's just an ideal example. So in this example, the voltage in the input voltage from the power source is 220 volts AC, and we have the voltage in the secondary winding, which is 110 volts AC as well. So remember that the primary winding is that one that will be connected to the power source, and remember that the secondary winding is the one that is connected to the load. Okay, but we would like to calculate the current in both sides. In order to do that, I would like to show you some basic formulas to do for transformer calculation. So in an ideal transformer, all the power that goes in will be equal to the power that goes out. The second formula that I would like to show you is that the voltage in the primary side divided by the voltage in the secondary side will be equal to the turn ratio in the primary side divided by the turn ratio in the secondary side. We can tell here that there is a directly proportional relationship between the voltage and the amount of turn of each winding. Okay, and the third formula I'm going to use is that the voltage in the primary divided by the voltage in the secondary winding will be equal to the current in the secondary winding divided by the current in the primary winding. We can tell here that this relationship is not directly proportional, okay, as in the second formula. Okay, so we are going back to the example, and we see that we have these three variables: voltage in the primary winding, voltage in the secondary winding, and we have the resistance of the load. Okay, by Ohm's law, we can say that the voltage will be equal to the current that multiplies the resistance, right? So by rearranging this formula, we can say that the current will be equal to the voltage divided by the resistance. So the current in the secondary winding will be 110 volts divided by 100 ohms, which would be 1.1 ampere. Okay, so we already have the voltage, the current in the secondary winding. Now we have two options. Remember that we have this formula here, that the voltage, that the power that goes in will be equal to the power that goes out. Okay, so we can calculate the power in this secondary winding, and remember that the power will be equal to the voltage that multiplies the current. So it will be 110 multiply 1.1, and the power will be 121 watts. So since we know that the power that goes in will be equal to the power that goes out, we can say that the power in the primary winding will be equal to 121 watts. We know that the power will be equal to the voltage times the current by rearranging this formula. So we can say that the current will be equal to the power divided by the voltage, which is going to be 121 watts divided by 220 volts. So the current in the primary winding will be equal to 0.55 ampere. Okay, so we solve the issue this way, but there is another way to calculate the current in the primary side. Since we have the both voltages and we have the current in the secondary side already, we can also use this formula instead to go by Ohm's law. So I will show you this other way. So we have that the voltage in the primary side divided by the voltage in the secondary side will be equal to the current in the secondary side divided by the current in the primary side. So by rearranging this formula, we end up in here. (110 volts divided by 220 volts and multiply 1.1. This will be equal to 0.55 ampere, which is equal to the current in the primary side.